All right. So, first and last name?
Lee Kong.
Lincoln. Okay. All right. Go by David, right?
Sure.
Thought that's what I read. Okay. All right. So we're going to start day 2 of this fun adventure. And just so you know, the video is now online. In case you looked, I will show you where to find that. If you log in to Desire to Learn or D2L, you'll find the news feed that's got the link to the video from Tuesday's recording. So you'll be able to pick those up at a later time. And as I finish with these, I'll post them. So I've got a channel, but I haven't shown the link for the channel. I'm just going to probably initially just link to the individual YouTube, so you'll be able to pick up anything that you might have missed. Okay, I do teach another section of this in the afternoon, but I don't have a recording capability there. So,
would you like us to subscribe?
no, right now I just got it unlisted, so I'll just put them out as a link. So, because I may be using it
really
for other.
big as the top math professor.
No, I'm not looking to gain anything, any kind of monetary perspective or anything like that. So don't worry about it. But all right. So anyway, you should be able to find that there. Remember again that if you go to the content section, see if I get to the content here. You should be able to find the homework that's due on the 29th. Okay. So remember the 29th, and that's just print it out, put your name on it, and fill it out, and you can turn it in at the beginning of class when you get here. All right? Okay. So any questions on any of those things, how to get to YouTube or how to get to the assignments? All right, cool. Okay. All right, so I'm going to go through a review of the inductive and deductive reasoning that we talked about last week. Seems like last week, just Tuesday. So what is the, when we go from the general to the specific, what type of reasoning is that? Deductive? Inductive? I've heard both votes.
I say inductive.
You say inductive?
Yeah, probably wrong, but hey.
Probably wrong.
Be confident.
Okay, it's deductive when you go from
I mean,
the general to the specific, right?
I said I was probably wrong.
Okay. So that makes this question pretty easy. So when we go from the specific to the general, what is this? Inductive reasoning. Now, remember the example? Probably the best way to remember this would be to think of the bird pictures, okay? The bird pictures, we looked at specific examples of birds, and from that we drew the conclusion that that birds have 2 feet, okay? That's inductive reasoning. So if you can draw that correlation, maybe that'll help you remember those, how to do that. Little memory technique there. All right, we didn't use this particular graphic, but we're talking general, specific, inductive, and deductive. So if I were going to put arrows on this circle that take me from general to specific, which would I draw for the inductive side? Which way would I draw the arrows, up or down?
Down.
Down. Okay, so on the inductive side, I'm going from the general to the specific.
No, you're going to the specific. Sorry, I thought, yeah, so down and then up.
Yeah. Okay, so we're going to go, right? So the arrows go this way, right? So from the inductive side, we're going from the specific situation. Let me see if I can pull that out of the way. We're going from the specific situation up to the general. Again, remember the birds, the pictures of the birds, right? And therefore, on the deductive side, we're going from the general to the specific, okay? That figure is also in your text. You want to look at that. Bless you.
Bless you.
Okay. We talked briefly about counterexamples. What type of reasoning does a counterexample apply to when we discussed it? Inductive. What was our counterexample that we had?
That not all birds can fly because penguins don't fly.
Penguins don't fly, and the penguin was the counterexample of the conclusion we reached when we looked at all the pictures of the birds that said they could fly, right? So the penguin is a counterexample there. Why is a counterexample important for us? And when we come to this kind of reasoning, why would you think that would be valuable to think about counterexamples?
A counterexample would give you the chance to find any flaws in your conclusion.
Would help you find the flaws in the conclusion. Okay, so if you don't have a counterexample, then that's going to lead you to believe that your conclusion is right. So the goal in any kind of inductive reasoning process is to find out if you can come to a counterexample to make sure that your conclusion is a valid conclusion. Remember when we talked about ellipses? What are the ellipses?
3 dots.
The 3 dots? Make sure I get it. What do they mean?
Pattern continues.
I'm sorry?
Pattern continues.
Pattern continues, right? So we talked about the natural numbers 1, 2, 3, 4. The next number is 5 because it goes up by 1. Okay. What about divisibility? When we say that one number is divisible by another,
They can be divided. So like, I don't know. I'm really not good with math, but something could be divided by another number, and it means like half, I guess, or it's like it's not gonna have a decimal. There we go.
okay, so not going to have a decimal, which means we're not going to have a remainder.
Yes.
Okay. All right. So 4, for example, 4 is divided by 2. So 4 is divisible by 2
There we go.
because there's no remainder when we do that division problem. Okay. All right. So induction. Another question on induction. Induction involves observing something and predicting something.
Observing patterns.
Okay. And what do we predict?
Conclusions.
A conclusion. Whoop. And if you could see that I could type, what type of reasoning is used in the scientific methods?
Scientific.
Yeah. What type of reasoning is used in the scientific method? We talked real briefly about that.
Is it deductive?
Go ahead. Go ahead. So repeat it.
Oh, it's deductive?
Deductive. Okay. Actually, both reasonings can be used in the scientific method, right? In one case, you're just kind of exploring. If you're doing it from an inductive side, you're looking at all kinds of examples, all kinds of specific examples, and trying to come to a conclusion. Okay? And you're looking for that counterexample to disprove it. Okay? So that's one example of a scientific method. The other is that you have a reasoning, a general observation that you want to then go find specific examples, see if you can prove. So both of them would be applicable in this case. Okay, prediction based on a specific observation is called a
Hypothesis.
okay. Hypothesis is one of them.
Conjecture.
Other
Conjecture.
conjecture. Okay. Okay. All right, so some examples, we'll go through some examples of inductive and deductive again to help us remember those. Okay. Every chicken that we've seen gets their food from the ground. Therefore, what conclusion could you draw from that?
They can't fly.
I'm sorry?
They can't fly.
They can't fly? Well, that is a conclusion you can draw, but probably not from that observation.
Maybe.
Therefore, all chickens get their food from the ground. Okay, every piece of music that we've heard has a guitar in it, therefore, we've got several musicians in the room.
It's country. No. Or rock.
All
All
music
music
is
has
music
guitars.
has guitar.
That all music has guitars in it. We're going to talk about that in a little bit.
Yeah. Explain dubstep. No.
Okay, each dog I've heard barks, therefore, all dogs bark. Every even number I've seen is divisible by 2, therefore,
Every even numbers.
every or all even numbers are divisible by. Okay? Each elderly person I know walks slowly, therefore,
Elderly people.
all elderly people walk slow.
You draw a lot of conclusions from
I'm certainly going to be walking slowly up Pikes Peak on Saturday. And my kids will bemoan.
Take a walking stick, call yourself Gandalf or something.
I had 2 walking sticks, but
Hey,
it'll
there
make
you
it go
go.
faster.
Yeah.
All right, so now, some of you are questioning this, right? Are these all valid observations? No. But these are valid conclusions that we've drawn from our premise, right? From what we've observed. So, does that mean every conclusion we can draw from a set of specific examples is going to be true? No. So that's the value of counterexamples, and that's one thing that's always important, especially when we talk about the scientific method, to test these things, because you're going to have people that draw conclusions all the time. Okay? We all draw conclusions. We all have conclusions about a variety of things, and therefore they may or may not be true. So we have to remember that they may not all be valid because the premise or the starting conditions may not always be valid. Okay? And so that's the second question. Does it matter that all these are valid in order for the process or the reasoning to be inductive? No. You can induce these things even if the results aren't right. Okay? So let's talk about deductive reasoning. Now remember on the inductive page, go back a little bit. A lot of what I said here started out with each. Okay?
Every.
In this case, it's a little bit different. Okay? A lot of them have alls. Thinking about that general case. All numbers ending in 5 are divisible by 5. So 45 ends in 5, therefore.
All numbers ending in 5 are divisible by 5.
Okay? Therefore, all numbers ending in 5 are divisible by 5.
45 is divisible.
Yeah.
And 45 is divisible by 5. Okay, so this is the specific case. So the number, when we talked about all numbers are divisible by 5, that's our general statement, our general perspective. So this is our specific case. Okay? All birds have feet. A robin is a bird, therefore
It has feet.
robin have feet. Okay, it's dangerous to drive on snowy streets, something we can certainly attest to around here. There's snow in the roads, therefore
It's dangerous to drive.
it's dangerous to drive. Or if you have a four-wheeler, it's fun. Not so much with a motorcycle. I did go over Vale Pass one time with it snowing. There was about 2 inches of snow on the ground on a motorcycle. My wife on back. That was a lot of fun. I was really tense by the time that was all over.
Living on the edge.
All cars have at least one windshield wiper. A Dodge Viper is a car. Therefore,
It has at least one windshield.
Dodge Viper has at least one windshield wiper.
Good too.
I had to be careful and think about this in the sense if I could have said two, that would not have been a valid general conclusion, right? Because there are some vehicles that only have one.
Yeah.
I'm going to use abbreviations, so. All right, all plants consume carbon dioxide. A rose is a plant, therefore,
Sometimes carbon dioxide.
roses consume carbon dioxide.
They would smell just as sweet.
I'm going to. Okay. So are these all valid?
Yes.
Okay. Now, does it matter? Does the validity and matter? Does the validity of the premise matter in order for the reasoning to be deductive?
Yes.
No. Just like in inductive, right? You don't always have to have a valid premise to get it to have the right conclusion for it to be an example of deductive reasoning. The process is what we're talking about here.
Oh.
You may pick the wrong data. You may use the wrong data. Okay. You may have a general conclusion about something and be wrong about it, but still come to a conclusion using the deductive process. Okay.
It seems like deductive reasoning is more sound than inductive, just from the examples that you
Yeah.
gave. Because in the inductive reasoning, a lot of them were not valid, but deductive, they were all valid.
Well, it could be just my choice of examples. Okay. The thing to think about from an inductive reasoning is if you're looking at specific examples, how many examples do you have to have in order to be able to be comfortable that your conclusion is a valid conclusion, right? We did just a random sampling of birds. We've all seen other birds in other environments, so we could make that conclusion about the number of feet they have, right? But you may have some other situation you're dealing with where you got, like we talk about DNA and fingerprints, right? That takes a lot of data for us to be able to come to a conclusion on that, right? So it's not that one is better than the other, they're just different. Any other questions on these? All right, so now we're going to go get into sets, into section 2.1. And by the end of this section, which is going to take us through the rest of the day, or the rest of the session, I should say, not the rest of the day. I don't think anybody wants to be here till 6 tonight working through
I was
these
gonna
sets.
say, I've got work, bro. I'm gonna have to leave.
Me too. Although I know you would all be interested in doing that, just because you would, right?
No. I'm gonna be truthful with that.
All right, you're going to be honest. All right, good. Okay. So what we're going to talk about in the sets is descriptions, how to describe sets, how to show them in a roster form, how to show them in a set builder notation, and those all have specific examples that we'll work through. And those are things, obviously, you're going to need to know for homework and quizzes and tests like that. Okay. We've also got some concepts that we're going to talk about in terms of sets, some basic concepts. What's a finite set? What's an infinite set? What are equal sets? What are equivalent sets? What's the cardinal number of a set? And we'll talk about the null or the empty set. And we'll talk about universal sets. Okay, so these are the things we're going to cover today. These are all in section 2.1. Okay. So, a set is simply just a collection of things. So what are some examples of sets?
T set.
I'm sorry?
T set.
I'm sorry?
T.
T? T sets?
Are we doing like real life things or numbers?
Whatever.
Okay, yeah, T sets.
T sets? So I'm having a hard time. Is that T like in the...
Like in
T-E-A.
the cups. And
Oh,
like,
T.
something like that.
Got it. Thank you. As I said last time, I may be slow, but I make a lot of mistakes, so you have to bear with me. Sometimes I'm hard of hearing. Okay, T sets, okay? What else? What are some other sets?
Number
sets. Number sets.
Number sets, okay?
Heard,
Those are pretty broad, so there could be lots of things in there. What was the?
no,
Oh.
it was a joke.
Okay. Other kind of sets. How about the students in this classroom? That's a set, right? How about the students in Front Range? That's a set.
It's very interesting. So,
How about the products inside the store at King Supers? Those are sets. Okay. So it's just a collection of things. Okay. And the relationship could vary depending on physical location, quantities, types, whatever. Right.
just for future reference, what's the difference between a suit and a set?
A suit and a set?
Yeah.
I wear a suit.
Like S-U-I-T? Oh,
Know what I
wait,
mean?
like in cars,
Yeah,
right?
yeah.
A suit of cars?
That's spelled the same way. Oh, it
The
didn't.
suit is like the individual, like the symbols, like heart and diamond and stuff. The set is like.
Because I've heard suit used in multiple forms. Like, okay, never mind. I'm thinking too hard.
Yeah, I'm not sure I'm following you on that one, but
Yeah, please don't.
like a suit of cards?
Yes.
Okay, suit of cards. A suit is not really a mathematical definition
Okay.
in that sense. Okay.
Well, I tried.
But the playing cards, 52 playing cards, could be a set,
Yeah.
right? It's a set of playing cards. So there are a variety of things like that. So again, don't overthink this. It's just a collection of things. Okay. The material, the products, the things that you have in your backpack is a set. All right. Things I have on top of the desk is a set. Now those things that are in that set are called elements or members. Okay? So each individual student in this room is a member or an element of the set of students in this room. Now there's a couple of definitions here that you'll need to know. One is well-defined. A well-defined set is something that you can clearly determine the contents for. Okay? Again, let's use the set of students in this room. Very easy to determine the contents, right? Because you can look around and you can see who's here. There's no guessing about that. We all know who that is. Okay? What are some examples of well-defined sets?
States.
I'm sorry?
50 states.
50 states, okay? You can tell where those states are. You know what those states are. They're well-defined. What else?
Like sets in a sports game. I know volleyball has like sets of 3.
Okay. Let's see. Yeah, because you could talk about, now when the tennis or volleyball or whatever talk about sets, they're not thinking about it from a mathematical perspective, but certainly that's an example because you can go back and you can show the scoring and the different maneuvers and stuff like that. So the number of professional tennis players is a set.
Like the actual elements,
The which elements?
like the periodic table.
Oh, the periodic table. Absolutely. Okay. So the elements in the periodic table.
Prime numbers?
Prime numbers. Okay. You can figure what those are. Okay. Has anybody heard about the calculation of pi? 2.14. Some of you may have heard about Pi Day, February 14th. Right? Because pi is the square root of 2,
Yeah, I
right?
was gonna say, wait, what? You said 2.14.
I said 2.14,
Yeah, I
didn't
was
I?
like, wait a minute.
1.14, isn't it?
If you want to go that way too, you know, we can round.
Okay, so how many elements are there? How many decimal places are there in pi? I'm sorry?
All of them.
Well, they're all of them, but we don't know how many of those are, right? Because they keep, I forget, they're up to like 1,000,000 and something and calculating right now, okay? Because you can never find the last decimal place in the square root, okay? Because it's called an irrational number. So if we were to try to say the set of all of the decimal places in pi, we couldn't do it because it's infinite. Okay? So that's not a well-defined set. From our class perspective, we're only going to deal with well-defined sets, so you don't have to worry about it. I mean, we'll show some examples later on with some non-well-defined sets. Any questions on that, on well-defined sets? Okay, so we talked about the students in this room as an example, the teachers in the school, the bills in your wallet, whether those are dollar bills or the bills that you owe the tax collector or whatever, the coins on your dresser, the objects in a cup of sand, the stars in the Milky Way, the furniture in this room, the tables, the chairs, computer sets, okay? Now, if you look at these, which do you think are well-defined sets? Remember the definition of well-defined sets? You can readily identify them, right? There's no question about what they are. So which of these sets represent well-defined sets?
Everything but the objects.
Everything but the objects, so you're saying this is not a well-defined set, okay?
I would argue that the stars in the Milky Way is not a well-defined set because it's really hard to count those.
Right. How can you figure it out, right? Because as soon as you think you've got them all, there's more, right? So I would agree with you. Not well-defined. Okay. So I think this is a good representation. Everything that we not marked here are well-defined sets. You can identify, we can go through and tell all the students in this room. We can go through and get the employee listing and get all the teachers in front range. You can open your wallet and see, what bills you have in there. You can go into your dresser, if that's where you keep your loose change, and see all your change that you have, okay? The furniture in this room, we can look at it, we can point, we can touch it. Those are all well-defined sets. But when you take a cup of sand, who knows what all's in there, right? There's some things that are microscopic that you can't see. So it'd be very hard to define those and put those in a list or identify them in a set. Okay? So any questions on well-defined versus defined or not well-defined? All right. So there's several ways that we can identify a set, or we can call out a set. There's a description, there's a roster form, and there's a set builder notation. And we're going to go through all those here over the course of the rest of the class. All right, so the description method is basically we're using words. We're just defining it in language format. So again, if you look at the previous page, I'm going to go back a little bit. Students in this room, those are words to describe the set. The teachers in this school, okay, so those are descriptions. So examples, we talked about those. Then the set contain the colors red, orange, yellow, green, blue, indigo, violet. That's the set. What set do you think that is?
The color spectrum.
Colors in a spectrum, in a rainbow, right?
Roy G. Biv.
Roy G. Biv. Right.
This is a song about him.
Red, orange, yellow, green, blue, indigo, violet. Colors in the rainbow. Again, those are words. We've used words to describe these. Now we'll see, this next one could be a little bit tricky, but we'll see about the car enthusiasts in the room. The sets containing the brands Ford, Chrysler, and General Motors is what? You almost got to be, in this day and age, you almost got to be a car historian to know what these are. American cars?
Muscle cars?
Muscle cars? It's called the Big Three. Just saw an interesting series on the Smithsonian Channel called The Cars That Made America. And they talked about the starting of Ford and General Motors and Chrysler. Very interesting. But it's the Big Three. Okay, so again, these are words that we've used to describe the set. There's another kind of a question. We'll see how what you know from a nutritional perspective. The set containing breads and grains, vegetables, fruit, dairy, meat, fish. What's that set?
The pyramid.
The pyramid. Okay, the basic food groups. Okay. Okay, so again, these are examples. We've used words to describe the set. So that's the description method. What do you think in terms of those being well defined? Are those well defined?
Yeah.
Yeah, they are well defined, aren't they? We know exactly what the colors are. We know what these elements are in this Big Three. We know what those basic food groups. Now you might get a question about some specific food. What kind of element is that? Is that fruit or whatever? But well defined. Okay, so looking at some more examples. What's the set containing the grades in this class? The possible grades. Give me the members. A is one. B. D. E.
E. No.
F. Okay?
Or troll if you're looking at Harry Potter.
Okay. How about the set of all the armed services in the United States?
Jeez. Army, Navy, Air Force, Marines, National Guard.
Army, Navy, Air Force, Marines,
National Guard.
Coast Guard.
Coast Guard.
Okay?
GG.
Yeah, it should be a. The set of all ways to legally obtain money. Legally obtain money. What do you think some example members of those would be?
Laundering. No, I'm kidding.
If you're doing laundry for
Yeah.
somebody, that could be
Yeah.
something,
That's
okay.
what
What- Work,
I meant.
Inherit?
inherit,
Gamble. Lawsuits.
gamble,
Alone?
loan,
Luck. Yeah.
and there's some others, right? Credit cards, and there are a variety of things like that, which you can consider a loan. Okay, the set of digits used in the after decimal point in the square root of pi is what? What are those digits?
You call them irrational numbers.
The irrational number, okay? But in this case, I'm thinking about, well, you're going to have a 1, you're going to have a 2, you're going to have a 3. We'd have to go look and see at the million or so to see which ones are repeated, which ones maybe not show up. Okay, but we're talking about basically you look at the decimal point in the square root of pi and you get whatever. Okay? All right, now the roster form method is a little different. Here we list the elements inside a set of braces, okay, and these are the braces that we use. We don't use parentheses or the square brackets. Okay, those are not used in set notation. So remember when we talked about the natural numbers, the counting numbers? So n equals 1, 2, 3, 4, 5, 6, and then the ellipses, the braces. Okay, so that is the roster form for showing the natural numbers. Remember the ellipses, the 3 dots? These are the continues on the same pattern. What would happen if we didn't have the ellipses and we just had that right there?
That would make it a set, right?
And we make it a set, still a set, but would it be the natural numbers at that point?
No.
No, because it's not inclusive of all those things after 6. Okay. So give me the roster form of the set that contains the counting numbers between 2 and 7. What's the first one?
2.
3, 4, 5, 6. And we said between because 2 and 7 are not between
Oh.
2 and 7, right? We'll talk about a condition, though, and how we can explain those in a little bit. Okay, now B is a set of counting numbers less than or equal to 36. So what would those be? Well, what's the first one? 1. We go 2, 3. Now we're going to be, rather than writing all these out, we're going to be a little bit shorthand. We're going to put the ellipses in. Okay? I'm writing uphill. But this is the way to show that in a roster form. Okay? You can see we started at 1. We showed the ellipses because the pattern, there's a pattern. It goes all the way up to 36.
Could you not start at 36 and do 35, 34?
You could.
Does it not matter, like, I'm assuming that negatives
I'm
wouldn't have
sorry?
any, negatives wouldn't have any play.
Negatives don't have a place because negatives aren't in our counting numbers.
Okay.
Okay? We don't have a -1 of something. So counting numbers start at 1 and go to infinite numbers. Okay? So, yeah, you can put these in any order. In fact, we'll have some examples where we show some of that. So this is a roster method. It doesn't matter what order you show them in. Okay? You heard about a roster for a sports team. What is that? That's the list of all the players on the sports team. Okay? Those can be organized in any form. That's another set of, or another example.
Included in a given team.
Okay? So, we talked about the big 3 automobile makers. So what's that set?
Ford, Chrysler, GM.
Okay? So this is the roster method of showing that set. What about the colors of the rainbow? Well, I'm not going to write them all out, but I'm going to show their abbreviations. Okay. Again, the roster method, we're just listing all the members. Now, from a convention perspective, we're showing them in this order, but they don't have to be in that order. They could be in any order you want them in, as long as they're all represented. That's all that counts. Remember on the previous chart we talked about the numbers between, I think it was 3 and 7 or whatever? Okay, but so we didn't include those numbers at the ends. A is a set of natural numbers between 3 and 7. This is an example we're going to use to talk about inclusivity. So when you're inclusive, when you put inclusive in the statement, that means you're including the first and the last part of your definition. Okay, so we said A is a set of natural numbers between 3 and 7. So A equals 4, 5, 6, because between does not include the 3 and the 7. Right? However, if we say that B is the set of natural numbers between 3 and 7 inclusive, then that now adds those in. Sometimes I do my 7 with a little bar through it. Okay? So inclusive just means if you've got some examples between 3 and 7, you throw the word inclusive in, that means we're now going to add those endpoints into our roster definition. Okay? Everybody understand that? Any questions on that? All right. So let's give the descriptions for these sets. Remember, descriptions are the words that describe a set. So what's the description for this set?
Even numbers.
Even numbers. So we're going to say it's even numbers, but that's not going to be sufficient.
Less than or equal to 10.
That's not going to be sufficient either, because even can be positive or negative, right?
They go up by 2.
Okay, so that's the definition of even.
Or
Okay,
Is it even counting numbers less than 10?
even counting numbers less than 10. That's a way to define it. Okay, there can be some other descriptions as well.
Wait, wouldn't it be less than or equal to 10?
Ah.
Because it's inclusive of
It
10.
has to include 10. Or we could have done it this way. And, yeah, whatever that means, but it means inclusive, right? Okay. There's some other ways to do that. You could say the even numbers between 2 and 10 inclusive. You could say the even numbers greater than 0 and less than 12. So there are a variety of ways to describe this and describe it accurately. Okay? So there's, in some cases, there's no exact one way.
So does that mean that if there were like ellipses at the end of like the number 10, that would not be inclusive?
That would not be inclusive. So in other words, if you had this set, 2, 4, 6, 8, 10, like that, okay, that means the pattern continues.
So it's not inclusive.
So it's not inclusive because you don't have an endpoint to include. But you could say that it's the even numbers greater than 0. That would be the description for this set, because you don't have an end to this pattern. Okay. All right. Everybody understand that difference? What's this set?
The physical value, or the value of coins above a penny.
Okay. The value of coins not including a penny. Okay. Are all coins that aren't pennies? There's a variety of ways to say that. Okay. What's this? Oop. This is a little tricky, I guess, for this class. I could say and what's that definition?
It's a room number and the level of the floor.
It's our room number for this class. How many elements is in that set?
2.
And this, how many elements? Just one, right? We just have that one list, one item in there, okay? How about this set? iOS and Android. What does that represent? What's the description of that set?
Operating systems,
Operating systems for
cell phones.
cell phones. Okay. Okay, any questions on this? Okay, so again, these are what method? What method are we using here to describe the sets?
Cross
the roster method, and we describe them in the method called the description method. Okay? All right, now we're going to start getting into set builder notation. So this funky E means that something is an element of. And the symbol E with the bar through it or the slash through it means it's not an element of. All right? So A equals 3, 4, 5, 6, 7, 8, 9, 10. What form are we describing this set in? What form is this set description? Roster. Okay. And what's the description of the set? How would you describe the set?
Counting numbers between 3 and 10 inclusive.
Okay, counting numbers. Between 10 and 3 inclusive. Okay, there's another way we could describe it too.
Counting numbers between 2 and 11.
Counting numbers between 2 and 11. Okay. So again, there's a variety of ways that you can describe sets that are still accurate and valid. Now, again, 4 is an element of A means 4 is an element of this set. 2 is not an element of A means 2 is not an element of the set A. All right? So, if we picked 100, what's the relationship with 100 in the set A? Is it an element of or is it not an element of? Not an element of. Right? So it's a pretty straightforward, is it or is it not? And based on that drives the selection of the symbols. Okay. Now obviously these are pretty straightforward sets, so that makes it a level of simplicity. Okay, now we're going to talk about another example here, the set of all the primary colors of light. It's not the colors in the rainbow. Okay. So what form are we using to describe the set?
Primary colors.
Okay, that's the
Yeah, what she said, description.
description. Okay. This is the description form. So what's the roster form of the set? Who are my computer monitor geeks or whatever? RGB. And any of you that sit around with old equipment, old TVs, you know the RGB numbers. Okay? And if you go and you're doing your little palette on like PowerPoint or some kind of computer software, you can go set, adjust the RGB in numbers from 0 to 255 typically to give you different color combinations.
Oh my gosh, now I remember that.
Now you remember that, huh?
Oh my god.
Was that a good
Completely
memory or a
forgot.
bad memory?
It was just me being exploring the TV and all.
Yeah?
Gosh, that was so long ago.
All right. Okay. So this description here, or this term, means that red is an element of the set A. Okay? I obviously didn't spell out the term there, but brown's not an element of that set, right? You don't see brown in that roster listing of any of the sets. So what are the other elements of A? We've talked about red. What are the other elements? Blue and green. Okay. And what colors are not elements of A?
Yellow.
Yellow,
Orange.
orange. And there's a whole bunch of them, right?
Chartreuse.
There's probably, I don't know what the latest computer monitors can show. There are millions of colors. Some of them are not really perceptible to the human eye, but there's still a lot of them out there. So we weren't gonna go through and try to do a roster method of all the ones because that would be really tough. In fact, would that be a well-defined set? All the colors that are not an element of A? It wouldn't be a well-defined set because there's too many out there, right? There's no way we could pick them all. Okay, tell you what. We'll just keep going through this one for a little bit. We'll do this page and we'll take a break. The set B is a set of all natural numbers between 5 and 9 inclusive. Okay, so that's the description. What's the roster form? Five, 6, 7. How far do I go? 8 till 9, okay? So that's the roster form of that set. Remember again, inclusive means we add those endpoints in there. Okay? So, is 6 an element of set B?
Yes.
Okay. Is 8 not an element of set B? No, because in fact it is. Is 5 an element of set B?
Yes.
Is 9 not an element of set B?
No.
Is 4 an element of set B?
No.
No. Is 11 not an element of set B?
Yes.
Okay. Now this is a pretty straightforward exercise because you can see the elements right there in that roster form. Makes it very straightforward to be able to see. All right, why don't we take a 10-minute break? A little bit longer than 10. We'll come back at 5 after by that clock. Okay? All right. And for those of you who came in late, let me make sure I got your... So Tony Dominguez? Jonathan? Holly? Okay, Jocelyn? Jonathan? Arlen? Oliver? Oh, I did have you covered, didn't I? I just didn't hear very well. Thank you. Zaira? Did I say that right? And Jessica? Did I miss your card?
Yeah.
Okay. Marvin?
Yeah.
Okay. A difference back there. Yeah, we're gonna collect these at the end of the class. All right. Now we're going to get into set builder notation. It's a little bit more rigorous, it seems. Sometimes it's called the set generator notation, and it can be used to symbolize a set. We use this typically in algebra, so if any of you have had algebra or we'll take that later. So this is the form, D equals, here's the open brace, X, such that some condition or set of conditions, close brace, okay? So this means set D is the set of all elements X such that the conditions, maybe singular or plural, X must meet in order to be a member of the set, okay? So it's kind of like these are all the things that have to happen for X to be qualified to be a member of the set, and we'll go through some of those examples. Okay, so let's take the set E. E equals the set of X such that X is an element of N. Remember what N is? Our natural numbers, 1, 2, our counting numbers, if you will. And x is less than 8. So if I'm going to draw the roster form of this, what are the elements in this set? What's the first one? 1. 2, 3. What's next?
Ellipses and 7.
4, 5. Where do I stop?
7.
7. Okay. And the reason I don't do 8 is because I don't have the word inclusive up here. Okay. If I had the word inclusive, then that 8 would be included in the set, in the roster set. So, what's the description? If I were to give the description of this set builder notation, what's the description of this set? Counting numbers. I'm sorry, you have to speak up.
Counting numbers 1 through 7.
Counting numbers 1 through 7. But there are other ways we could say that too, right? We could say the counting numbers less than 8. And it's kind of almost a clue a lot of times in your set builder notation. Some of these conditions will help define the set. So as you're looking at these different problems, you can use that as a clue. Another one is, it could be the set of all counting numbers less than 7 inclusive. Okay? So there's a lot of different ways. So there's no one right way to describe these sets. Okay, so let's say F is a set of all elements x such that x is an element of even numbers and x is less than 9. Well, first of all, is this legal? We're talking about even numbers, but we're throwing 9 in there. Is that legal to do that?
Well, we aren't including 9, are we?
We're not including 9, so sure, it's okay to put it in there. Okay, doesn't matter that it's not even itself. Okay. So what's the roster form of this?
2.
Well, it's kind of interesting, isn't it? Because we talked about even numbers, but we didn't talk about even natural numbers, did we? Oh, so there's a little bit of a trick in this one, isn't there? Okay, so to make it easier on ourselves, we're going to start at this end and work backwards. Well, do we include 9? No, because it's not an even number, right? So let's start at 8, 6, 4, 2, 0, -2. Okay? A little bit of a trick. Now, if I had said they were the even natural numbers, we're going to call that f prime, okay? Then f prime would equal 2, 4, 6, 8. All right? So that's what's the difference between the first set and the second set. So what's the description of this? How would we describe this in English?
All even counting numbers less than 9.
No? What are, some other thoughts? Holly, right? Okay.
All even numbers less than 9.
All even numbers less than 9.
Not done.
I'm going to abbreviate numbers. Here with me. Okay. All right, so that's the description of that set. And again, if we had the f prime, which was 2 through 8, even numbers 2 through 8, we could have said all the even numbers greater than 0 and less than 9. All right, so now we have f. It's a set of all elements x such that x is a member of the negative whole numbers and x is greater than negative 7. Okay? Negative whole numbers and x is greater than negative 7. So what's the roster form of this? What's the first one? If we start by negative 7, what's the first number? Negative 6. What's the next one? Negative 5, and we're just going to keep increasing. Where do we stop? Negative 1? Is 0 negative? No. So we don't include 0 in there. Okay, so that's the roster form of this description. The negative whole numbers, and x is greater than negative 7. All right. By the way, if we go back to this one, is this a well-defined set? Remember our definition of well-defined?
No,
It's not a well-defined set. And why is it not a well-defined set?
because it uses the
You
ellipsis.
can easily name them all, right? Because it just keeps going infinitely. Right? How about this one? Is this a well-defined set?
Yes.
Okay. All right, so what's our description for this?
All negative whole numbers greater than negative 7.
Set of all negative, can't write today. Negative whole numbers, what's the rest of it?
Greater than negative 7.
So can you see the real similarity here between the set builder notation and the description? A lot of clues there. So as you're working your problems and all, you can use that as information to help you. Similarly, if you're given a description and you're asked to produce the set builder notation, remember the definition that you have here, because this can help you form that set builder. Okay? They're obviously very closely related. Okay. So, F is a set of all elements X, such that X is an element of furniture types in this room. So what's the roster form?
Desks, chairs.
Anything else? You got a desk up there, so we got the desk covered. We got the chairs covered.
Phones, laptops, whiteboards.
Okay, it depends on how far you go with the definition of furniture, right? Okay. We certainly have tables. You're all sitting at tables. Okay. You can, if you include whiteboards, that would be another explanation. But
Are tables and desks not the same thing?
I guess it depends on how much of a purist you are. I view them to be different.
Okay.
Okay.
By that definition, wheels.
So we'll leave it at that. So what's the description? What's the description of the set?
Classroom furniture.
Sorry?
Classroom furniture.
Classroom furniture. Okay, it's right up there. The furniture types in this room. Okay? All right. Okay, now there's some fundamental set concepts we're going to talk about here. So finite sets are sets with no elements, or the number of elements is a natural number. Remember natural numbers? They start at 1. They go up infinitely. Okay? But the sets with no elements, or Number of elements is a natural number. Okay, give me a set, a finite set. What's an example of a finite set? I'll give you an example. You won't know these, but these are the sets that are my children. Okay? It's a finite set. Okay? You can count them, right? 1, 2, 3, 4, 5. Okay? What if I said that I want to give you the set of all of my children who are older than 100 years old? How many members would there be in that set? 0, right? There wouldn't be anybody in that set. I may be old, but I'm not that old. Okay? So that's a case where there's no elements. Okay? A finite set. Infinite sets are those sets which we can't count. So what's an example of a set, an infinite set?
Decimal places in pi.
Decimal places in pi. Or, in a mathematical term, irrational numbers.
Stars in the universe.
Stars in the universe.
Question.
How about if I said a set of all the students in all the schools in the whole world? What do you think? Is that finite or infinite?
It's finite,
Finite, right? Because it may be a big number,
but it's
but you can still count them, right? Might take you a while, but you can still count them. What's another infinite set?
All the kids in all the schools in all the world from here on.
Okay, good. So all the kids that ever were students and will be students. So a finite or infinite number, right? I mean, you think what's the population of the world today is like 5 billion or something like that? Okay.
it's too much.
And it's going to keep growing, right? So, and you throw all those generations in there, so that's a large number. Okay, so everybody get the idea, the difference between a finite set and an infinite set? Okay.
Just the way that the definition for finite set was worded.
It sounds a little weird.
It was very confusing.
Yeah. Okay, so let's talk about some examples here. The set F, where L is a set of x, such that x is a natural number and x is greater than 5. So what's the roster form of this?
X equals 6.
7, 8 ellipses.
Where do I stop? You don't stop, right? So this is where the ellipses come in. So what's the description? What is a description of this set? I'm sorry?
All numbers greater than 5.
All numbers or all natural numbers? Okay? And is it a finite set? It's not really a finite set. I mean, you could count them if you could count that high. You just keep counting, right? Because as soon as you count the last one, there's another one. Right? So it's really an infinite set. Okay, so x So the set A is the set of elements x such that x is a negative whole number and x is less than 0. What's the roster form of this?
A equals. Start with -1.
Okay, we're going to start with the -1.
-2.
-2. How far are we going to go? Forever, right? So what's our little cheat sheet for doing that? The ellipses, right? That's our little cheat.
I have a question.
Yes.
Considering the way we look at negative numbers on a number line, it goes like off to the left, right?
Yep.
Can you start with ellipses and then say
No.
go -3, -2, -1, and then end it?
No, you can't. And the reason you can't is because of the definition of ellipses. Remember what ellipses stand for? The continuing pattern, right? Is you're based on a pattern. If you got the ellipses at the very first piece, you don't know what the pattern is yet. Right?
Yeah, because we read left to right.
We read left to
Yeah,
right.
okay.
It's the same with English too. When you're writing like a paragraph, you can't start with the ellipses. You have to like start with a sentence or two and then do the ellipses if it's too long when you're quoting, and then continue so you get the point across quicker. Because if you don't know what the beginning is, it's kind of difficult to understand
Right.
the end.
So just like the English language, we do that when we write English, okay? What's the description of this?
All negative whole numbers less than 0.
Okay. So I need somebody other than Brent to help me with this one.
Sorry.
What's the description?
Don't everyone speak at once.
All negative whole numbers less than 0.
All negative, it's the set of all negative whole numbers in fact, this is kind of redundant, isn't it? Because by definition, if it's negative, it's going to be less than 0. So I don't need to include that. Infinite set or finite set? Infinite set.
Infinite.
Okay, so B is a set of elements X, such that X is the element of the floors in the Front Range Community College. Okay, what's the roster form of B?
C, B, A.
What's the description of this set? Floors in the Front Range Community College, right? So,
Of the Westminster campus. anyways.
good definition there. I didn't even catch that.
Are we talking about the main building or the whole college? Because if so, we're forgetting D in the greenhouse.
It's not a floor.
Yeah, good point. In the main Westminster building.
I try to. I don't know. I get too overthinky and I have to be precise.
Good to be precise. I tend to be very myopic in my thinking. There's no other campus in Westminster, right? No other building than this building. Okay, finite set or infinite? Finite, right? We can count these. This is pretty straightforward.
Or finite. Let me see.
Okay,
We say infinite, we say finite.
so here's for the football purists in the room. Okay. So C is a set of all elements X, such that X is a member of the leagues in the NFL. So what's the roster form?
AFC and NFC.
Sorry?
AFC and NFC.
AFC and NFC. Okay. So what's the description of that? And even those of you who don't know football should be able to figure that out.
All leagues in the NFL.
all leagues in the NFL. Okay? Finite set?
Yep.
Yep, you can count it. All right, now we're going to talk about some other elements of sets. The equal sets are sets who contain the same elements. Okay? So we say that A equals B if and only if set A and set B contain the same elements. Now, order isn't important. Okay? So let's talk about the floors on Westminster campus, the main building. We said they were A, B, and C, right? I could also say, well, because I come in on the main floor typically, or the top floor, they're like that. Or I can say that I usually come in at this floor that we're on here and go upstairs, but I hardly ever go to the dungeon. I go to floor A. Okay? So these are all equal sets. They happen to be the same set, but they're all equal sets. The order is not important here. I can put them in any order. So they have the same elements. Any questions about equality of sets? All right. Guys, look at that example. We've seen that recently. So does A, B, C, the set containing the elements A, B, and C equal the set containing the elements C, B, A, and B?
Yeah.
It does, right? So yes. All right, how about from a set builder notation? Okay. So the set of all elements X, such that X is a natural number and X is less than 15, and X equal, or X is an element of the set X such as, excuse me, X is an element of N, the natural numbers, and X is less than 15.9. Are those equal?
Yes, because they're natural numbers, right?
They're natural numbers, right? So yes, they are equal. Okay. I just used something that was not a natural number as the endpoint and saying it was less than. Now, if I had said inclusive, 15.9 inclusive, that would have made it for an interesting discussion, wouldn't it? Right? Because you, by definition, want to include 15.9, but it really isn't included in the set because it's not a natural number.
Yeah.
Would not have changed the outcome.
Wouldn't that be a false statement because the natural number directly below 15.9 is 15, and the other one is not including 15.
Ah, good. Yes. So everybody hear what Holly said? Okay. So this is really not, these are really not equal, are they? And why aren't they? Because what's the natural number closest to 15.9 to the left, if you will, on the number line? So, Holly's correct. So these are not equal, okay? And not because of the 15.9, but because here you would have 1 through 15, here you'd have 1 through 14. Now, if I said inclusive on this, they would have been equal. Okay, everybody get that? Okay. How about these? The set where X is an element of the natural numbers and X is between 2 and 11, and the roster form 3, 4, 5, 6, 7, 8, 9, 10. Are these equal?
Yes.
Okay. How about this next one? X is a negative whole number and it's greater than a negative 10. And the set of all negative whole numbers between negative 9 and 100 inclusive. So the first one, you got a negative whole number, and X is greater than negative 10. So what if I were going to do the roster form of this, what would the roster form of that be?
-9, -8, -7, ellipses. Wait.
All the way till -1.
Yeah.
Good. Okay. What would the roster form of this next one be? my endpoint going to be on this set? I'm hearing votes for 100, but I'm hearing a vote for.
-1 because it's negative whole number.
It's a negative whole number, right? So, a little bit of a trick there, okay? Because everything 0 and beyond are positive. Or 0 is not negative or positive, but beyond that. So they aren't included. So, now, are these equal? Yes, they are equal, okay? So, if on the surface you're looking at a problem and you can't determine if they're equal, try to do the roster form and see if you can figure that out, because that may help you visualize whether or not these are equal. So yes, they're equal. How about the set of all colors in the rainbow equal the set of primary colors of light? Remember we talked about those. Are those equal sets? No, they're not, right? Because colors in the rainbow, red, orange, yellow, green, blue, indigo, violet. The primary colors of light were red, green, and blue, right? So, different sets. Any questions on these?
Question.
Okay.
Okay, so take that last one.
This last
What,
one? Or
yeah.
this?
What would you, the color one, what would you refer to one set, like, okay, so the primary colors of light, right? That's a set.
Well, let's do the roster form, okay?
Yeah.
So what's the roster form of all the colors in the rainbow?
R, comma, O, comma, Y, G, B, I, V.
Roy G. Biv, right? Okay, what's the roster form of the primary colors of light?
RGB. So, is there a term for which when one set is inclusive of another, but, so the first set is inclusive of the second set, but the second set is not inclusive of the first set?
This set is contained in this set,
Yes.
okay? This set is not contained in this set, right? So what we say, and we'll get into this later, I'm sure, is that this is a subset of this, okay? Because it's some elements of the major set, and in fact, we'll talk about universal sets in a little bit. This would be a universal set, could be a universal set, because you could argue that all the colors in the spectrum are variations of these. Okay. All right, any other questions on this? Okay, so now we're going to talk about cardinal numbers. They're not the names of the, or the numbers of the football, or the baseball players on the St. Louis Cardinals, okay? Or the Arizona, the Phoenix Cardinals, okay? Arizona, I guess would be. The cardinal number is a set of the numbers of elements in a set. Okay, so if I have 4 elements, its cardinal number is 4. Okay, so I write that is n of A is the cardinal number of the set A. N is cardinal number of A, where A equals 1, 2, 4, 8 is 4. Okay, so there's 1, 2, 3, 4 elements in that set, and therefore the cardinal number of that set is 4. So we also say that set A has the cardinality of 4. What's the cardinality of this set? 3, okay? And so I could say, since I haven't given it a set number, I'm going to do it this way. All right, let's see this one. So what's the cardinality of this? Of this set here, the roster form? 7. Okay. All right, so basically all you do is you count the number of elements in the set, and that gives you the cardinality. That's the definition.
When there's those 3 dots, does that count as 1, or do you just count the number?
That makes it really tough, doesn't it? Because if you have 3 dots, so if I do this is infinite. Right, I can't really count those, right? Because those are just keep going on forever and ever and ever. But what's the cardinality of this? 7. Okay? So it depends on where the ellipses are as to whether or not you can count or not. If they're at the end and you've got an ongoing pattern, you can't really count the number. But if they're in the middle and you've got an endpoint, you can count the number. Okay? All right. So tell me the cardinality of these. What's the cardinality of the first one? 3. Okay. How about this one? Natural numbers less than 15. 14. Natural numbers between 2 and 11. 8. Okay. Because 2 doesn't count, but 3, 4, 5, 6, 7, 8, 9, 10. How about negative whole numbers greater than minus 10? 9. Okay? And the way we would do that, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4. You can do it the other direction as well if you want to. And then we just count them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. How about the set of all primary colors of light? 3. RGB. Okay, now there's another term that we deal with on sets called equivalent sets. Okay. Sets are equivalent if they have the same cardinality. Right, so we say set A is equivalent to set B if and only if the cardinality of A equals the cardinality of B. So,
and this is different than equal sets because it's only looking at cardinality, right?
only looking at cardinality. Are these equal sets? See the question mark I have over the...
They're equivalent sets.
They're equivalent sets because they have the same cardinality, right? The cardinality is 3, but they're not equal. Now why aren't they equal?
Different elements.
You have different elements in one set than you do in the other. Okay? Are these two sets equivalent? This set and this set, are those two equivalent?
No.
So we say x is a natural number, and it's between 0 and 9. So that means 1, 2, 3, 4, 5, 6, 7, 8. So what's the cardinality of that number, of that set? 8. What's the cardinality of this? 6. Okay, so they're not equal in cardinality, so they're not equivalent. Okay, Now, here's a special relationship here between equal and equivalent. Two sets that are equal also have to be equivalent. And why do you think that would be?
Because they have to contain the same elements.
They have to contain the same elements, so by definition, they contain, oh, we won't go back that far.
So if one set has 7 elements, then in order to be equal, of course, the second set is going to have the same 7 elements. Therefore, the cardinality is 7.
If two sets are equal, what do we know about the sets?
They have the same elements.
They have the same elements. So by definition, what's their cardinality? Is the cardinality equal?
Yeah.
The cardinality is equal. Okay. So if they're equivalent, can they be equal? Equivalent means they have the same cardinality, right? Look at this one. Did we say this one? These are equivalent?
Mm-hmm.
These are equivalent, but they're not equal,
No.
right? So if you're equal, by definition, you're going to be equivalent. But if you're equivalent, you're not going to be equal. Okay? All right. They require to be equal, they have to have the same cardinality and members. To be equivalent, they just have to have the same cardinality. Okay? All right. So I've got some sets up here. A, B, and C. A is a set of 1, 2, 3, 6. B is 6, 2, 1, 3. C is RGBY. D is car, bus, horse, train, plane. E is plane, boat, mule, buggy, motorcycle. So is A equivalent to B? Yes. They have the same cardinality, which is 4. Okay. Is A equivalent to C? Yes. Same cardinality, 4. A equivalent to D? No. This has a cardinality of what? 5. And this has a cardinality of 4. Okay. I should be taking my notes up here, so. Is A equivalent to E?
No.
Why not?
Cardinality is different.
Cardinality is different. Is A equal to B?
Yes.
Yes. Now what do we know about A and B? Their cardinality is the same, right? Do they have the same members?
Yes.
But the members are in different order.
Order doesn't matter.
Doesn't matter, right? Doesn't matter. Okay. How about A equal to D?
Wait.
No.
You.
Oh, did I skip one?
Yeah.
Is A equal to C?
No.
Cardinality is what?
4.
For each of them, but do they have the same elements?
No.
No. Okay, A equal to D? Nope. They have the same equivalence?
No.
Nope. So by definition, we don't even have to go forward to look and see if the members are the same. Is A equal to E?
No.
Same thing, right? Different cardinalities. All right, so we got the set G, where X is the element of A, B, C, D, and E, and the cardinality of G equals 4. Yeah. What does that mean? So X is an element of that set, and the cardinality is 4. Can we do this? Can we solve this? Can't solve it, can we? Why not?
They don't have the same cardinality.
This has some element of 5. Now what we could do
You.
is we could draw different permutations, but they're really not going to be the same. So this is not solvable, is it?
I was gonna say, if you were doing a problem like this, the cardinality would always have to be bigger than the elements of the set for that to be possible.
It wouldn't have to be
You know what I mean?
bigger,
So,
but in this case, if I did this, now can we solve it?
yes.
Okay, and what would the roster form be? It's right there, right? Just
Yes.
happens to be in the set builder notation. Okay, So now we say H has this, X is some element to this set, and X is a set of transportation types. Can you give the roster form of H?
Would it just be 5 different kinds of transportation?
Well, so X has to be a member of this set, right? So those are the subject. X is an element of that, and X is a set of transportation types. Is there a set? Is there a solution for this? Is there a?
Well, if, like, how we just do Roy G. Biv, like, just use the first letter, like, could it not just be, like,
Oh,
airplane, bus?
well, that's interesting. That's an interesting thought. So these are not abbreviations, just one.
It's either D or E because of the equations above.
Okay. All right. So what if we take these in terms of these sets up here? Okay. Now let's think about this in terms of those sets. Okay. So X is an element of basically any of these sets and a set of transportation. What's the roster form of this? So you take each of these sets. What's the roster form going to be? Well, you have to look at the roster form up here, right? Because D and E are included in this set description. Okay? So in this case, if we're not just looking at these letters, but we're looking at these as sets, then they're going to be these two sets, right? Okay? Everybody got that?
It's a bit.
Question?
No. It's takes some time to understand.
Okay. All right, so now we have some other sets. A, B, C, D, and E. Okay? All right, we got about another minute. Let me see if I can go on. Tell you what, we'll finish this up. We'll cover this in the next, start this with the next class, okay? All right, so let me get your attendance card as you walk out. Well, let me stop this for a minute.